Okay, so we're going to get started then. The idea is to do as much as we can. I'm going to go I'm going to try to get 1 through 12 at least. Tomorrow in class we can look at 13 and 14. So 1 through 12 is the goal. 1 through 12.
Size is the prize. Goal is the goal, size is the prize. Let's get it. It's games are long. It's lots of fun. Let's go.
Okay, number 1. The effect of acid rain upon the yield of crops is of concern in many places. To determine the baseline yields, a sample of 13 fields were selected, and the yield of barley, grams per 400 meters cubed, so squared, was determined. An output from SAS appears below. SAS is a statistical software program, and it gives you information on a sample that looks a lot like what you see in front of you. So we have N is 13. We have a mean of 220, standard deviation of 58. Even though it doesn't say the standard deviation of the sample, there's no way that could be the standard deviation of the population. So it has to be of the sample. So we want a 90% confidence interval. Notice that this is meant to be a multiple choice question, not really a free response. So we're just going to kind of shortcut our way through it. We're not going to go through all of the stuff. We are going to need 1 and 2. So the first step here is to figure out center of the sampling distribution, mu, and this is x bar. That's going to be exactly equal to mu, and we're going to be approximating that with, what is that, 220, 231? Okay, number 2 is sigma of x bar. That's exactly equal to sigma over root n, but we're going to approximate that with the, what is it? Thank you. 58.5721 divided by the square root of, what's our sample size? 13? 13. And that's what we get there. So that's actually all the stuff we need for the shortcuts. We need to know the margin of error, and that's going to be, well, what do you think, T or Z? T star with 12 degrees of freedom multiplied by 16.245. So let's go ahead and pull up the calculator. Ooh. There is no need to go through all 4 steps. Okay, so what do we need? We need inverse T. Inverse T of, yeah, confidence interval. We want a 90% confidence interval. We have degree of freedom, it's 12. So that's 1.782. How come it's not multiplying for me? That's bizarre. Anyone have that number?
28.
953. Good. And so we get the mu. That's going to be equal to 220.231 plus or minus 28.953. Let me get that plus and minus in there.
For all the funny answers on these, will you make it like Z star instead? Like what you would get if you used C star instead?
Oh, for the...
For the fake it.
It's possible.
Answers.
I'm sure you didn't like to hear that one.
So yeah, why didn't we use the star for this?
Because it's the sample. Like the mean and the standard deviation are only for the single sample of 13.
Yeah, but if you had the population, then why would you be doing it?
Exactly.
So why did we have to use these?
As a building block.
So
Baseline.
basically, you're not going to use it on tests.
You really, I mean, if you're doing actual statistics, you're not using Z-star, ever.
So you're doing actual statistics.
This is pretty good, pretty close.
So like who knows?
Hmm?
So like who knows?
No.
We use Z star for our
For proportion always, but if we're talking about a mean, it's very unlikely that you're going to use Z-star. Okay, any thoughts on question 1? Great, I like that. Let's look at question 2. We have, you want to compute a 90% confidence interval for the mean of a population with unknown population standard deviation. Sample size is 30. So the key here is unknown population standard deviation. So that means you're going to use a T-star, and this is not that crazy. You just need to remember that you have a 29 degree of freedom. And so we would go back to our program. We're going to do the exact same thing. 90 degree confidence interval, 29 degrees of freedom, right? Which sounds like the 29 well, what was I going to... What is that movie? That 50 Shades? 50 Shades? Yeah. 29 degrees of freedom. The sequel to 50 Shades of Grey. 1699. Whatever. I didn't want to know that my mom was reading it. That's for sure. No. Okay. Next. To assess the accuracy of a laboratory scale, a standard weight that is known to weigh 1 gram is repeatedly weighed n times, and a mean x bar of the weighings is computed. Suppose the scale readings are normally distributed with unknown mean mu and standard deviation sigma equals 0.01. Okay, now that they told you sigma is 0.01, that should signal to you to use a Z-star. How large must n be so that a 95% confidence interval has an margin of error of 0.0001? Is that right? Okay, so let's get our formula here. We know the margin of error. Margin of error is equal to, in this case we're going to use Z-star because we know sigma. Z-star multiplied by the, no, not by the square root, by sigma over the square root of n. Z-star for 90, correct me if I'm wrong, that's 1.645. Multiplied by, we're told that sigma is 0.01.
Oh, this is the one where they said X bar in the first half, and then in the second half they said sigma.
Yeah.
So you would just.
So they're saying sigma instead of x.
Yeah. So if you kind of read through this, okay, they're telling you that the mean is unknown, that mu is unknown, but somehow they have a way to figure out sigma. Okay. I don't know. That's weird to me. Right. So we have this equation here. We know we want the margin of error here on the left. We want the margin of error here on the left to be less than 0.0001. You can solve this by hand, of course, if you wanted to. I don't care. But for my purposes, I want to use a solver. So math, go to the solver. So we want the margin of error is going to be equal to z, and in this case, it's going to be z multiplied by, then that, I think I can get a fraction here, right?
Yeah.
Sigma.
Mine doesn't.
What should I use for sigma? Using s might be confusing.
How about
Use
quotation
Q.
marks?
Q.
I think Q's a good one.
That's a good one.
Q. Okay, so we'll use Q for sigma. It looks like an upside down sigma, doesn't it?
That's what I was thinking.
90 degrees.
Over the square root of n.
Whoa.
What?
Here's that dinosaur.
Okay, so we want the margin of error is 0.0001. Z, we said that was 1.645. Sigma is 0.01. And so now we just have to solve for n. Remember the trick here, two tricks. First thing is make sure that you have a sensible guess for n.
Wait, isn't Z not that?
It's not?
Because it's 0.95.
0.95? Oh, it's not. So it's 1.96, right?
Yeah.
My bad. 1.96 means I have to change this right here. 1.96. Let's go back to the calculator. Change z to 1.96. Okay, does that value of n, is that a pretty good place to start looking? I think it's fine. As long as it's not negative, you're okay. So let's alpha solve. That's trick number 2. In order to solve, you need to use alpha. Why is my cursor not moving? Alpha. Enter. It looks like we have 38,416. That's a pretty big sample.
So it's okay if the answer is, because the answer in the back is 38,414.
It also randomly says 17,000.
Okay, so it seems to me that you'd want n to be
The answer in the back is too low than that. Is that?
It's rounding.
okay. So what are we saying? What are we saying?
The answer in the back says 38,414.
What did we do wrong? What did we do differently?
I don't know, because couldn't like 1.96 be more specific?
Use the program.
Maybe.
There's no program.
Maybe.
Because, like, yeah.
So yeah, the thought might be maybe at some point we used a different z that was to carry to more decimal places. That might be it.
But we're right. Right now, we're good right now.
Yeah, I mean we solved it correctly for what we have. I'm not exactly sure why the back answer key says what it does. But as far as I'm concerned, we solved this correctly. And again, this is a multiple choice test. So if you're pretty confident, find the one that's closest. What happened? 384? Did you push alpha enter? Okay, any last thoughts here with this one? Okay, we're gonna, yeah.
How do we know that we're using C star?
We know we're using z because they gave you a value for sigma. Specifically says sigma equals.
Okay.
Okay.
If they don't, then we're using T star. Yeah. It's pretty good.
Okay. Okay. Let's move on then. Number 5? Number 4?
Wait, there's a second one.
Oh, there's a second part. Oh, yeah. Interval width of 0.0003. We would go back over here and just change this to a 3.
Wait, wouldn't you change it to point or 1.5?
Hmm? Oh, the width is 3, so 0.0003 divided by 2, right? Okay. Just so that we're clear on what we mean by margin of error and width and all of that business and how they all work together.
Yeah.
Let's imagine on a number line, let's imagine we have a number line with our, I don't know why I chose that color for the number line. That's embarrassing. Okay, in a number line, this would be mu, or that would be x bar, and the distance from here to here would be the margin of error. That's the margin of error from here to here, and then also from here to here. That's what we mean by x bar plus or minus the margin of error. This right over here, from end to end, that's the interval width. So visually looking at that, the interval width is 2 margins of errors. No, 2 margins of error. That's grammatically sound, right? Margins of error. Anyways, that's... Did I solve it? No, I didn't. Alright, so if we know the interval width is 0.0003, we just have to divide that by 2. By the way, you can put 0.0003 divided by 2 here. No problem. And then alpha enter again to get n.
No math.
17073.
Well, because you're squaring.
Okay, let's move on then. What are we on? Number 4, right?
Yeah.
Okay, 4 says the weights of 9 men have a mean of 175 pounds and a standard... No, what did I just do? The weights of 4 men have a mean of 175 pounds with a standard deviation of 15. What is a standard error of the mean? Okay, so standard error. Let's remember what standard error is. That's equal to sigma x bar. And that's going to be equal to, or approximately equal to, S over square root of n. What's happening? Why is this not working anymore? Okay, so what is S? S is 15. What is N? 9 men. So 15 divided by square root of 9 should be 5.
So the X bar is just given to confuse you. The X bar is just given to confuse you.
Yeah. Okay, any more thoughts on 4? Okay, let's look at 5. So we have a 95% confidence interval is going to yield the following. 95% confidence interval is 44.2 to 54.2. I think what I'm going to do is I'm just going to go ahead and do that same diagram that we had before. Let's try and take a look at the... Let's take a look at this interval on the number line. Okay. On the number line, we have, on this side, 44.12. On this side, we have 54.2. Oh, did I mess that up? 44.2, and we have 54.2. So that's this over here. This is the interval width from there to there. Right in the middle, that's X bar. Also, this is a margin of error, and this is a margin of error. But to answer this question really quickly, the X bar is always going to be the midpoint of the interval. Mathematically, you could find the midpoint just by finding an average. So if I do 54.2 plus 44.2, that's 98.4. 98.4 divided by 2 is 49.2, I think. So X bar should be 49.2. Where is... oh, here. That's equal to 49.2. So X bar, that's going to be equal to 44.2.
Mr. Curry, can you just find the difference and divide by 2?
Yeah.
That's the answer.
Well, I don't know. If you found the difference, then that would be 5.
That would be the interval. Yeah. Like, if you find the difference, that's the interval width, and then you divide by 2 and you have the margin.
Okay, Clive, I didn't realize you
Oh, but if you divide by 2, if you divide by 2,
Do you want me to get up there?
no, it makes sense.
I'll go
Yeah, I mean, that gives you the margin of error, but that doesn't give you X bar.
But it's just asking for the margin of error.
Is that for the margin of error? Okay, margin of error is 5. 6. Oh, we get to use some calculator, huh? The level of dissolved oxygen in a river is an important indicator of the water's ability to support aquatic life. If you collect 20 milliliter water samples at 15 randomly chosen locations along a stream and measure the dissolved oxygen. Here are your results in milligrams per liter. Check the assumptions for a T-interval. Construct and interpret a 95% confidence interval for the mean dissolved oxygen in the stream. So I don't know about you reading this, but as I read this, it sounds like I'm supposed to do all 4 steps here. So we're just going to do all 4 steps. Mu. What are we trying to figure out? The mean dissolved oxygen level of the stream. Okay. Okay, let's get our variables. Do we have a number for x bar? No, we don't.
We have to put in the stat.
We don't have an S. I'll bet we have N though. No, we don't even have an N. Oh, we do. It's 15. Okay, so go ahead and put those numbers in the calculator. I'll go ahead and do that as well. Second, no, not second. Yeah, second. Quit. Stat. Edit. I'm going to clean up L1. And then I'm going to start writing these down. Does someone want to be the village reader?
1.53.
Thank you.
5.04.
Uh-huh.
3.29.
Uh-huh.
5.23.
Whoa.
4.13. 5.
Wait, after 3.29 is 5 point...
23, sorry.
It's okay.
4.13. 5.5.
Mm-hmm.
4.83. 4.4. 5.42. 6.38.
Mm-hmm.
4.01.
Uh-huh.
4.66.
Good.
2.87. 5.73.
And
5.45.
okay. I'll slow down here. Okay, home screen. I need to calculate, so I'm going to go calculate one of our stats. The sample oxygen levels were in L1, so I'm ready to go. It looks like I get 4.77. And just to make sure we know what we're talking about, are we using S or are we using sigma? That's good. So 4.77 and 0.940. 4.77. And I already forgot what this was. 0.9.
0.940. If you round it, it's 0.940.
Okay. Okay, so that's everything we need for the first part of this. Next part of this is everything about the sampling distribution. So the first thing about the sampling distribution is the mean. So mu x bar. That's exactly equal to mu. And that's approximately equal to 4.77. Don't worry, I'll get that approximately there. Good. How can I say that this is true?
Random.
What does it say in the question?
It said randomly chosen.
Randomly chosen locations must mean SRS, right? It probably doesn't mean SRS, but we can't do anything unless it is an SRS. So we'll have to assume that will suffice for an SRS. Part 2. Sigma x bar let's see, we're going to have to approximate that with 0.940 divided by the square root of the sample size. What's our sample size? 15, yeah. That looks good to me. Okay. Do we have a condition here for this standard, for this? Yes, we do. Good. 20n equals, that's 20 times 15, which is 300, yeah? Okay. Do we know how many randomly, do you know how many locations there are along the river? Should be infinite, yeah. So, there must be, yeah, there must be more than 300 locations along the river. Most likely there are more than 300 locations, considering the nature of the river. You can pull up a sample in plenty of places along the river. Last one, 3. The shape of X bar, that should be approximately normal with a mean of 4.77 and a standard deviation of 0.243. What am I looking at? Yeah, thank you. How do I know that this is a normal distribution versus a sampling distribution? Do I have a normal population? No. Do I have a large sample? Oh crap, that means I have to do the other one, right? Okay, so let's take a look at the normal probability plot. Make sure that looks normal. We quit here, we go to stat plot. Normal probability plot, plot on. That very last one is normal probability plot. My data is in L1. It doesn't matter where I use a data axis. Then we're going to use everyone's favorite zoom, zoom 9. Ooh. Why does it look like that?
Mine looks pretty
Why'd you
good.
change that?
Even a lot.
You should zoom 9. I think you're supposed to zoom 8.
Yeah.
Should be zoom 9, yeah?
Yeah, I did 9.
Ah, there we go. There she blows. Does that look pretty good? Okay. So just to, once again, I know we did this during period 3. We didn't do it quite like this in period 2. But we're saying the sample is approximately normal. Or no, let's start over again. The normal probability plot is linear, approximately linear. Therefore, the sample is approximately normal. Therefore, the population is approximately normal. Therefore, the sampling distribution is approximately normal. Yeah, I think if you just draw an arrow, you're fine. And actually, if you just wanted to say that you can just kind of shortcut this and say the normal probability plot is approximately normal, therefore the sampling distribution is approximately normal. That's perfectly fine. But if you want to make your AP reader cry, it's so beautiful. The normal probability plot is approximately linear. Therefore, the sampling distribution is approximately normal. That would be probably your shortcut way of writing it. Just remember that that one statement is, how do I say this, is short-circuiting a long chain of logic. Okay, so that's everything about the sampling distribution we're going to need. The rest of this comes pretty quickly. We have the margin of error is going to be equal to a t-star with 14 degrees of freedom multiplied by the standard error. Do we know the t-star of 14? Someone have that number? That gives me a margin of error of 0.5212. Is that right? That means you have mu should be equal to 4.77 plus or minus 0.521. Good. Did someone do the addition subtraction already? Actually, I have the answer key, so let's cheat. Do you want to use this as do you want to write this as an interval or as an inequality? Interval. Wow, you all are pretty great. You know what? Mu epsilon 4.25? 5.29? That's pretty great. Okay, that's the end of part 3, the math part. And then the last part is to write some kind of a summary. So the mean dissolved oxygen level is between 4.25 and 5.29. Do we remember the units here? Milligrams per liter? Milligrams per liter. We used a method that successfully captures mu.
This is crazy. This is the multiple choice question. How to bring it home now.
95% of the time. I also want to remind you, since this is supposed to be part of the multiple choice test right here, there is so much here that you don't actually have to do in the scope of a multiple choice test, okay? If you're doing a multiple choice test, you need exactly 3 numbers to get this done, or maybe 4 numbers. You'll need to know X bar, you'll need to know S, you'll need to know T star, yeah, and you'll need to know N. That's it. Once you get those 4 things, just calculate away. Okay. Any other thoughts on 6? Let's look at 7. A polling organization announces that the proportion of American voters who favor congressional term limits is 64%, and the margin of error is 3%. Oh, this is actually a multiple choice question.
Wait, what?
I thought it was ordinary.
This is a multiple choice question. So let's say what's wrong with these. What's wrong with A? If the poll were conducted the same way again, there's a 95% chance that the fraction of voters favoring term limits will be between 61 and 67%. Remember that margin, or that confidence level, has to do with success rate of capturing the mean. If you are doing a lot of samples, those samples are not all going to be identical, but 95% of those samples will contain, those intervals created will contain the value of the mean. That's different than what this is saying here. This is saying that there's a 95% that the interval created is going to be 61 to 67. That's not quite true, right? B. There's a 95% probability that the true percentage of voters favoring term limits is between 61 and 67. That's a weird one too, because there is a number that is the true proportion that favor congressional term limits. It's a number that was decided before you even started taking a poll. So either it is between 61 and 67, or it isn't. We don't know which one it is. It's not a 95% chance. Either it is or it isn't. C. If the poll was conducted again in the same way, there's a 95% probability that the true percentage of voters favoring term limits would be within 3% of the percentage favoring term limits in the first poll. That just sounds like a mess to me, actually. Among 95% of the voters, between 61 and 67% favor term limits. No, the thing that makes that wrong is that among 95% of the voters. That's not really what confidence means. I mean, the best sounding one from these is B, but I'm not very happy with B either. What is it supposed to be? E, none of the above? Oh, good. Okay, yeah. None of the above.
Yeah.
Remember, confidence level is a success rate. There's a 95% probability that we captured the mean, not 95% that the mean is between these two numbers.
So what would be like the correct statement using all
You could say something like, if this poll was conducted many times, 95% of the confidence intervals created would contain the actual value of the mean. That would be correct.
So 64 and 3 have nothing to do with 95%.
No, they don't. Remember, because it's about the success rate of the method, not about the actual numbers. Okay, let's go to 8. We have a random sample of 900 individuals selected from a large population. 180 of them are regular users of vitamins. Thus, the proportion of regular users of vitamins in the population is about 0.2. What would be the standard error of this approximation? So let's remember standard error here is, standard error here for us, this means sigma of p hat. And that's equal to, and I should write the formula, standard error is equal to the fraction of p times 1 minus p square root, my bad. Where's my square root? So that's p, 1 minus p, the whole thing divided by n. That's standard error. So for us, that means what is that? 0.2 times 0.8. The whole thing divided by the square root of 0.2 times 0.8 divided by 400. Am I right on that? 900. .0133. That's standard error. It's pretty pleasant sounding. Okay. Let's take a look at number 9. Number 9, we have 95% interval for pi. Pi. P, the proportion of Canadian beer drinkers who prefer Red Lion, was found to be 0.236 and 0.282. Interpret this interval in context. So basically this is asking you to just write the conclusion based on what you see here. So the conclusion should be something like the proportion, you could put true proportion too. The true proportion of Canadian beer drinkers isn't that how you spell the hockey club? B-I-E-N?
I think it's the French one.
So yes. The true proportion of Canadian beer drinkers who prefer Lion Red. Which sounds like Voltron to me, but whatever. Is between 0.236 and 0.282. A method was used that successfully captures the population proportion 95% of the time. That sounds like what you would write in your 4-step summary or your 4-step problem, right? Sure it is. Of course. Okay, 10. Z star for a 70% confidence interval. That's ridiculously easy. If you're using the program, we want an interval, confidence of 0.9, 1.645.
0.7.
Okay, if you want 0.7, you'd put a 0.7 there, and you get 1.036. 10. Z star equals 1.036. Did I remember that right? Yeah, I did. Also remember that you're probably going to have to also memorize that if we have a 70% confidence interval, that means the tail areas are both 0.15. So if you wanted to use the old way, you can second distribution inverse norm. That tail area, like we said, was 0.15. The left tail is 0.15, the right tail is 0.15. The central area is 0.7, that adds up to 1. And that gets you 1.036. So either way is good. 11. A 95% confidence interval for the mean population computed from a random sample is found to be 9 plus or minus 3. We can conclude that, okay? So this says to me the true mean of the population is between, was that 12 and 6? I should probably say 6 and 12. The method used successfully captures the population mean 95% of the time. And that's 11. Sound good?
Yeah.
Thank you, Sivan. Dose. Oh, this is where we're stopping, right?
Wait, can we skip number 12 and do number 14?
We're going to do 14 class.
These are supposed to do.
12. 95% confidence interval for the mean reading achievement score for a population of 3rd grade students is 44.2 to 54.2. That sounds familiar. Where did we use those numbers before? Question 5, huh? Imagine that. Suppose you use a 99% confidence interval for the same information Will the new interval be wider or narrower? What say you? If you want to be more, how do I say this? If you want to be more confident, do you think you should make the interval smaller or make the interval bigger?
Small. Small.
Think about it like this. Let's say you were playing basketball and you want to be more confident you're going to make the shot.
So make it larger.
Would you make the basket bigger or smaller? You make it bigger,
It's smaller.
right? That means you have a better chance of being correct. So, exact same thing here. We want to make our basket as wide as possible. We want to make the confidence interval bigger so that we have more of a chance of being right.
When would you want to make the confidence interval smaller?
If you need specificity. Okay, so a 99% confidence interval would be bigger. 99% confidence interval will be, what's the word that they use here? Wider. And will carry less risk of being incorrect. Does that basketball analogy work for everybody?
Yeah.
Okay.
That's me, your aspects.
Last thoughts? Okay, there's no more pizza, so tough luck. You can eat the box. It's fine. I'm sure it's good for you in some way. It's probably better for you than the pizza.